Now, we can certainly have more than one material or more than two materials, and realistically we would have, because that calorimeter that I showed you a little while ago, of course that calorimeter is going to heat up. Not the whole thing, but the interior cup is going to heat or cool with the water. There's good thermal contact there, and that's an aluminum cup. So what I'm going to realistically end up with is I'm going to have something that I'm dumping in here, some water, and then the calorimeter. So again, all I have to do is say, okay, well, I'm going to have Q of the unknown material, whatever it is, material, plus Q of the water, plus Q of the calorimeter. And again, all those together just equal 0. And I need to know the calorimeter is going to start at the same temperature as water does, because once I pour that water in there, that's what's going to be governing that. And the warm material is coming from somewhere else. Could have more than one material. I could throw a chunk of silver in and a chunk of gold. I could throw, chunks of many different things. Wide variety of options that I have here. So I'm going to do an example here where I'm just going to use copper. Assume that the calorimeter is aluminum, and I'll put down the specific heat for aluminum right here. And I'm just going to make up some stuff here. So bear with me as I work these numbers out a little bit. Let's say that I have, let's go a little bit different than what we had before, get more realistic. I'm going to say I have 50 grams of copper, and let's say that's sitting at 100 degrees C. Let's say that I have the calorimeter is 75 grams of aluminum. That's the calorimeter. This is the material. And that's going to be sitting at whatever temperature the water is. We're going to say our water is 20 degrees C. And then I'm going to have 200 grams of water at 20 degrees C. And I'm going to set up this equation. So I'm going to leave those numbers there while I write those into the equation up above. All those Q's are going to equal 0. So my first one, I've got 50 times 0.092. And then here again, that's that delta temperature. I don't know where it's going to end up. T is where it's going to end up. Everything's going to end up equilibrium. T minus 100 for the copper. My calorimeter term, I've got 75. 0.215 is the number I've asked you to take. And T minus, well, T minus, it's going to be the same temperature as the water is, so T minus 20. I need more space for this anyway, so I'm going to get rid of it. Equals 0. And then I got 200 grams of water, so that's 200 times 1 times T minus 20. And all those together equals 0. So, let's see. This looks like 4.6 T. All right. 5 times 0.92 sounds a lot like 4.6 T minus 460 plus, I'm not even going to hazard a shot at that in my head. $16.125 T minus 32.25, little decimal in place, 322.5 plus 200 T minus 4,000. Again, I collect like terms, and what you notice here, again, the water really drives the bus here. Look how small those other values are in comparison to what's going on with the water. So I got 220.725 T, and adding those others up, this was 322, so that's 4782.5, and T will equal 4782.5. 21.67. Now this is pretty remarkable, really. I mean, you think about, oh, we got the stuff going on, we got 100-degree stuff, doesn't matter. We got stuff sitting at 100 degree, and it has such a low heat capacity that it just isn't very hard to cool it down. It doesn't have a whole lot of energy to give. Doesn't heat that water up very much at all. 1.5 degrees, that's all we see. So as I set up this experiment, which eventually I'm going to do, I need to make sure I don't end up with this kind of situation, because we don't have the kind of accuracy to be able to measure a difference between 20 and 21.6 degrees. right? We need to make sure that the water temperature is moving more like it did in the previous example, so I need a bigger mass of whatever else is going on, because these just, you know, the aluminum and the copper together just don't make as big a contribution as the water does.